Welcome to today's lesson continuation. This is the final class for physics, and if you have made it this far, I must tell you this at this moment to congratulate yourself. You're almost done with physics. We are going to continue with electrical energy and power, because normal power in physics and electrical energy / power has a little bit of difference. There is a little nuance between those. You have power in other part of physics, but you have power too in electricity. Is that electrical power that we are looking at? Electrical power and energy. Though in our last class, I talked little about electrical energy, but we are going to look at it in depth in this class. All right. So electrical power and energy. Electrical power and energy / energy. Okay. All right. Electrical power, the rate of work done in an electrical circuit or an electrical system. Electrical energy is the ability of an electric current to do a work, right? To perform a task, depending on what is imposed in the system. So starting with electrical power, we have how many formulas for electrical power? I think the most common is 3. We have power, P is equal to I square R. Power P is equal to I V. Then power is equal to V square over R. I think this is the final one. All right, where R equal to resistance, P equal to I equal to current. All right, V equal to what? EMF or volt. Okay, measured in volt, right? All right. So this is the formula for power if you are asked to calculate power in an electrical component. The way we are calculating energy, we can say E. Sometimes this electrical energy can be represented with W. E is equal to, I'm just making it easy so that you can always remember. E is equal to I VT or VIT, anyone. E is also equal to I square RT. Then the final one, E is equal to V square T over R T over R. All right. So these are the formulas for, so depending on what you are given, all right, where I is equal to current, V is equal to EMF input or potential difference. This V can also be potential difference. Okay. Then T is equal to time. T is equal to time. R equal to resistance. All right. So depending on what you are given to solve with, for example, you are given in your parameters, you are given potential difference or EMF, you are given time, and you are given resistance. This is the most suitable formula to use, because you can't see any other formula that has all these parameters in it. All right, so that's that for that. Also, this one, if you are just giving only current, volt, and time, this one is going to be better. If you are giving current, resistance, and time, this is going to be what? Better. All right. In our last class, we talked about resistance. Okay. Looking at electric power, 1 horsepower is equivalent to how many watts? 746 watts. It's actually 745.7 watts. But let's put 746 watts. Then 1 horsepower is also equal to, if we are measuring in kilowatts, it is going to be 0. Because of the watts to kilowatts. That's 0. That is there. 0.746 kilowatts. All right. So take note of all these. They always set question for them. Then there's a sweet formula for power loss. If you want to calculate power loss in a system, this is the formula you are going to apply. All right. Power loss in a system, an electric system. Let us look at power transmission for domestic use. Not just only domestic use, power transmission for domestic and industrial use. All right. So power transmission involves the transmission of power that has been generated in the power station, the one we call NEPA. Okay. So when power is generated in the power station, there is a particular procedure they follow when they want to transmit that power. Because if that procedure is not followed, a lot of energy is going to be lost. Power is going to be lost, thereby impeding efficiency. All right. So this procedure is what they normally follow. And this question is very, very common. Very common. So transmission of power, method of transmission of power. How is power transmitted? Okay. From power station to the users. All right. Which is industry and also domestic use like you and I. Electricity is generated at power station. So the first thing is that at power station. All right. That's where it's generated. After generation at power station, what happens next? Step up transformer steps up the voltage. All right. So step up transformer steps up the voltage. That's what is stepped up. Then after that, what happens next? As this step up transformer steps up the voltage, the current is what? Reduced. Reduced current. That's what the step up transformer does. It steps up the voltage and reduce current. You know why? Because when electric current is transmitted at a low current and high voltage, it reduces the amount of energy lost by heat. If you transmit electric current at a high current, you transmit electricity at a high, or you transmit power at a high current and low volts, you are going to lose a lot of energy as heat. All right, through the conductor. But what the power station normally do is that they use a step-up transformer to increase. That's why you see transformers along the road in your street and so on and so forth. They increase the volts to the highest they can increase it. Then they reduce the current. What does that? Step-up transformer does that. All right. And when the voltage increases, transmitted through the high volts line, the one you call high tension. Okay, transmitted through what? High volts or voltage line, the one we call high tension. After the transmission, what happened? It is now time for domestic use, right? You now see step down transformer. So step down transformers now step it down. Step it down to what? To suit domestic use. All right, domestic and industrial use. So the step down transformer does what? It reduces the volts to suit domestic use and what? Once again, increase the current. All right, that's why when your transformer is 40, especially the secondary coil of your transformer, you start noticing that in your streets, when they get half current, okay, the current is not full. You start getting low current, okay, because the transformer wasn't able to what? To elevate the current and reduce the volts. Though it reduced the volts, yes, but it's not able to elevate the current. Sometimes you can get a volt that is very high, okay, high voltage. Immediately you on any of your appliances, everything will just burn. Sometimes the transformer now increases the current too much. All those are 40 secondary coil of transformer. All right. We are going to look at the part of transformer that is responsible for these conversions. All right. It's very easy. All these are common questions. Very common. So step up. The part of transformer that's responsible for step up is the secondary coil. The part of transformer that is also responsible for step down is secondary coil too. It's also secondary coil. So both step up and down in a transformer serve as a source of secondary coil. So the parts of a transformer. Let's look at the part of a transformer. Okay. We have soft iron core. Okay, which is the source of magnet. All right, for magnetism. Then we have primary coil. We have secondary coil. Then we have insulator. So these are parts of transformer. All right. Let's just say it's a part of transformer. So how do you know if it's transformer, if it's step up transformer or step down transformer? It all depends on the number of what? The number of coil. Okay, number of coil. Or the wound. Okay, number of coil. Because it's the secondary coil that step up voltage and reduce current, step down voltage and increase current. So when the current is stepped up, voltage what? Is reduced. When the current is stepped down, voltage is what? Increased. So voltage is inversely proportional to current. Current is inversely proportional to voltage. So as voltage increase, as current increase, voltage reduce. As voltage reduce, current increase. As voltage increase, current reduce. So that's it. Inverse proportionality. Now, we've already talked about the function of the secondary coil. All right. So what is the function of the primary coil now? The function of the primary coil is to receive current. Receive current and induce what? Induce electromagnetism. The function is to what? Induce current, number one. And number two, receive current. Sorry. To receive current, that is the first one. Receive current, then number two, induce electromagnetism. That is responsible for the conversion of current or for the step up or step down of current in the secondary coil. So the current usually gets to the what primary coil first. Then, like I said before, either what makes a transformer a step up transformer, a step down transformer depends on how many coil you have, how many wind you have in the secondary coil. Okay, how many coil, the number of coil. Okay, so the number of coil, what I put here, determines if it's going to be called a step up transformer or a step down transformer. In a step up transformer, because we are stepping the volts up, okay, the coil is usually smaller. Okay, step up, smaller coil. All right, then step down, more coil. All right, more coil. So that's that for transformer. Okay, so how does transformer work? Like I said, I just explained how transformer works. When you send because you use the transformer for either set or step up or step down. All right. So when the current is placed in the transformer, the primary coil receives the current to be stepped up or to be stepped down. And when it receives it, it induces an electromagnetic force. Okay, it induces an electromagnetic force that transfers the current to the secondary coil to be what? To be converted to either a higher volt and lower current or to a lower volt and higher current, depending on the type of transformer, either a step up or a step down transformer. So transformer works under the principle of electromagnetism. So electromagnetism, which is a magnetic field induced by the induction of current. Okay, electric current induces magnetism. All right, current induced magnetism, that's electromagnetism. So most of the time in electromagnetism, contact is not required. Contact is not required. That's why some objects, you might have not touched that object and the object greens you. It shocks you and your hand you haven't touched that object yet, but it shocks you. For example, ring boiler or boiling ring. Sometimes when you are using it to boil water, you might have not even touched it and it gives you some, some wake up shocks. That's what it occurs as a result of what? Electromagnetism. Electromagnetism. That's what I just explained. Who is the father of electromagnetism? His name is what? Faraday. Michael Faraday. He is the what? The father of electromagnetism. And electromagnetism okay, so a current through a conductor, when current is passing through a conductor, let's say this is a wire, when current passes through a conductor, heat is generated, like I said, and that heat is loss of energy. That heat that is generated is measured in joule. Okay, heat energy, joule. All right, and what is the application, okay, of this heat generated? The application is in electric heaters slash kettle slash pressing iron. Okay, then you have incandescent bulb. What is incandescent bulb? That old bulb that used to be yellowish in color. So it's the heat produced that is used to light. Okay, that's what induces the light. The heat produced from the conduction of electric current by a metal called tungsten. Okay, tungsten. It's a transition metal used in incandescent bulb. All right. Then the final one is what? Fuse. And you know that fuse breaks. Okay, it helps to protect our device, safety device. All right. So when the current is high, the heat produced become high, so it melts the component of the fuse and the fuse break the passage of current. That's it. With that, the device is protected from such current surge that might have destroyed the unit or the system. All right. So normally, fuse usually protects our devices, okay, because it melts at a high current. So when the current is high, fuse melts. All right. And when the fuse melts, the current line or the circuit is broken. When fuse melts, the current line or the circuit is broken because fuse is part of the circuit. Fuse closes the circuit. So when the fuse melts, the circuit is now open. Okay, it's now open. So that's what we see. The fuse rating of fuse now. When we want to rate fuse, we rate it based on the maximum current for the circuit. That's that maximum current that is capable of destroying the circuit. That's what we normally use to rate fuse. All right, and there is a different arrangements involved in fuse. Most of the time we normally use parallel arrangements in those, but parallel arrangement is better than series arrangement when it comes to fuse. Okay, when it comes to fuses, I will give you some advantage of parallel arrangement. Okay, that's parallel arrangement. Okay, that's branches, arrangement with branches, like I explained before. All right, parallel arrangement. I will give you an advantage or advantages of it. Number one is that each appliances get full supply because they are all branched. They get full supply each. Failure of one doesn't affect the other. If you do a series connection now, a series arrangement like this, if this fuse fail, this one, since the source of the current is here, if this fuse fail, this one will not work. But if it's in parallel, because they are branched, if one fails, the other will still work because they have branch here and they have branch here. They are branched, right? If one fails, others will still work. Another one is easier to control. Okay, easier to control. All the devices here, you can control this one separately because it has its own separate fuse. You can control this one separately because it has its own separate fuse. You can control this one separately. But here, it's just one fuse because it's what? Series arrangement. Once this one burns, you can't control the other ones on your own. You can't control all these ones. You have to use one fuse, just like having one switch for all the lights in your house. And this one, this series connection, is like, say, having different switch for each light in your house. So if you want to off, if you want to off any light, you just go there and you put off the light, and that's that for that. All right, and usually it's more efficient and safer. This parallel connection is more efficient and safer. Okay, so do well to answer the questions you find in your in the lesson notes. Now let's look at magnetism and magnetic field. Very easy. I am going to make this very easy as possible, and we have to be very fast. We have not much time. Okay, magnetism. Okay, let's just say magnets / magnetic field. All right. What is magnetic field? Magnet is a substance that induces magnetic field. What is the magnetic field now? Magnetic field is a space or an area whereby the repulsion and attraction force of a magnet is experienced. As simple as that. The repulsion and attraction of a magnet is experienced. We have the North Pole. It usually occurs from the North Pole to the what? To the South Pole. All right. Magnetic field flows from North Pole towards South Pole. From North Pole towards South Pole. All right. So, and there's a law that binds magnets, just like the Coulomb's law. It states that like pole, because they are the same, they repel. All right. Like not will repel not can never attract not. Okay. They repel. Okay. Opposite. South again is another one. South, they repel. They can't marry. They are gay. Okay. Then unlike pole, like north and south, pole attract. All right. So in each pole of a magnet, like for the South Pole, for example, there is something called dipole. This is the dipole. This part and this part, the two. It's dipole. In each of the pole, they have their own dipole in each of the pole. That's the opposite pole. So you are going to understand the need why you have to know this dipole, why you have to understand what it means. All right. Let us look at types of magnets. We have natural and artificial magnets. Natural and artificial. That's artificial now. Man-made. All right. Example of natural magnet is lodestone, the popular lodestone. That is usually black. That black lodestone, that black magnet you always see, that's lodestone. All right. Then artificial magnet is an example. Is like bar magnet and horseshoe. Bar magnet and horseshoe. Horseshoe magnet. All right. So, looking at the properties of magnets, based on the type of magnet, okay, or based on the material of the magnet. So, artificial magnets are made from either soft iron core or steel. So, let's now bring artificial magnets now. They are made from either soft iron core. We are talking about the material, iron, soft iron, or steel. All right. So for soft iron, this one demagnetized easily, easily lost magnetism. But for steel type of magnet, it retains its magnetization for a long period, or a magnetism retains magnetism for a long time. All right. Hope you copy. Okay. Now let's look at magnetization and demagnetization. How do we create artificial magnets? How do we demagnetize? What we have magnetized, how do we demagnetize it? How do we break magnetism? How do we form it? So we are looking at making and breaking of magnetic field or magnetism. All right. Remember, magnetism is the ability of a substance to attract other substance. That's magnetism. All right. Magnetization. All right. The ability of one substance to attract another substance. That's the ability of a magnet to attract an ion with a free dipole. That is why some metal like aluminium are not attracted by a magnet. Why? Because it has no free dipole. Okay. It has no free dipole. So, because it's the dipole that is in charge, the dipole in each pole. For example, we have north pole. I said you have dipole here. The two pole, dipole. All right. Dipole. The dipole. All right. So, because aluminium as a metal, it has no free dipole on its own, it cannot be magnetized. Okay. It doesn't. But for iron now has dipole. All right. That's why iron are easily magnetized. All right. So, method of making magnets is to stroke with another magnet. So when you carry lodestone now, we are looking at making magnets. All right. So when you take lodestone now and rub it on iron for some time, you get what? Artificial what? You get artificial magnets. All right. That's one method. That's the major method of creating a magnet or forming a magnet. This works under the principle of when you put an object closer to another object, that object begins to what? To possess the property of that object. Okay. So when what they call iron sharpen iron. So iron sharpen iron, when you bring something that is sharp closer to another thing that is sharp, or something that is sharp to something that is not sharp, that is a blunt object, you start, noticing that that object or that substance begins to what? To possess the property of the substance that it never had. That is the principle at which the making of magnets through what? Contact or rubbing works under. All right. Now let's look at demagnetization. Demagnetization or breaking magnets. Demagnetization or breaking magnet. How do we do that? The first one is hammering. I forget something here. When we are making magnets, okay, making of magnets. Okay, we also have another method of making magnet. There are two in number. Okay. The second one is electrical method. Okay, that one got in from electromagnetic induction. Okay, electrical method. Okay, which involves what? You induce current and magnetism is generated. All right. This is usually done with direct current. Don't forget to DC. Electrical method with DC, direct current. So hammering, hammering towards the what? Towards the north pole. Towards the north pole. All right. Number two way of breaking magnet is what? We can use heat to break magnets or demagnetization. Heating it. That your lodestone, that your black magnet, when you take it to the fire and you heat it for long at a high temperature, it's going to lose its magnetism. If you want to experiment it, experiment that at home. Then the third one is what? Electrical method. You can see that you can use both electrical method to make and break magnets. So the difference is that here we'll now use alternating current. All right. Alternating current to demagnetize it. All right. When you bring the magnet close to alternating current, that's changing current. The difference between direct current and alternating current is that direct current is just a steady volt. No change. The volt is just steady. Steady current, delivering steady current. But alternating current changes. Okay, with demand. All right. As demand changes, alternating current changes. That's why in an alternating current, you can put a positive wire to a negative wire and put a positive wire to a negative wire. You interchange them. You stick on your current source or your power source, and nothing happens to your appliances because it's an alternating current. The current is going to alternate it to match the demand, to match what is needed. That is alternating current for you. That is alternating current. All right. So you have to be fast. Now let's look at the method to keep a magnet. Okay, to keep a magnet, keeping a magnet. How do we keep magnets? That's preventing a magnet from losing its magnetization property. All right. The first one is what? Use magnetic keeper to store the magnet. Use magnetic keepers Magnetic keepers are made of what? Soft iron core. All right, they are made of soft iron core. All right, another one is avoid hammering, avoid heating, and avoid dropping. All right, because when the magnet falls to the ground, it's also like hammering. It's going to give the same effect as hammering. Okay, because it's a trauma, it's a disturbance. All right, so avoid it dropping on the ground, because if it happens several times, you start noticing that the magnet is now losing its magnetism. Now let's look at the flush pattern in some, flush pattern, okay, in various material. Okay, magnetic flush pattern in various material. You have to be very fast. No time. The class should not be more than 1 hour. We have exhausted 30 minutes already. So now, flush pattern in, the first one that we are going to look is flush pattern in a current carrying conductor. Okay, for example, you have a straight wire like this. What is the flush pattern in this current carrying conductor? It is what? Concentric. Okay, concentric, it occurs in a concentric circle. Okay, concentric circle, something like this. Just round the wire like this. Concentric circle. Take note of this. Round the wire like this, concentric circle. That is the flush pattern. Then the next one is flush pattern in a, let's do solenoid. Okay, let's do circular wire first of all. Flush pattern in a circular wire. In a circular wire, what do you see? Let's say this is a circular wire. Let's just use 2. What is the flush pattern in a circular wire? The flush loops around the wire. All right, it loops around the wire, just around the wire. Okay, around the wire. That's the flush pattern in a circular wire. All right, so it all depends on how the wire is. Wait, let me do something similar to what we have in the lesson notes. Okay, for better understanding. So this is a circular wire. Okay, 1 circular wire, then 2 circular wire put together. Maybe they want to use it to form a coil. Then what is the flush pattern here? The flush pattern is we just loop around the wire. It loops around the wire like this, around both wires like this. You see, this is the flush pattern at which it moves. It just loops around the wire. Okay, loops around the wires. All right. Then the third one is in a solenoid. In a solenoid, you know that solenoid is a wounded instrument. Okay, having soft iron core and windings. It could be copper winding or whatever winding. Okay, it's a coil instrument. All right, so in a solenoid, what do we see? It mimics that of the earth. Okay, having a north and south pole. All right, that's for solenoid. It usually mimics that of the earth. It's usually what? Uniform. That it flows through a certain style. It has its own style. Okay, it's uniform. Resemble that of it's not that of the earth, it's that of the bar magnet. Okay, like bar magnet. All right, one pole forms the north, the other forms the what? The south. All right, just like that in a solenoid. All right, so a solenoid is something like this: north pole, south pole. All right, this one is a solenoid. All right, so it moves from north towards south pole. All right, so this is the flush pattern. All right, is uniform. You see one as north pole, you see one as south pole. To test polarity here, we use what? We use Fleming right hand rule. Fleming's right hand rule. All right, that's how we determine the polarity. Also, in this is it circular wire or concentric? In this concentric too, we still use the Fleming's right hand rule. Okay, to determine polarity here in these two. Okay, for current carrying conductor and solenoid, we use what? Fleming's right hand rule. Before we understand what a Fleming's right hand rule is, let's do the final one, which is flush pattern of magnet placed in the earth field. Okay, magnet in earth's field. Earth's field. All right, what do we expect? It's like that of the earth. Flush pattern of the earth. What is flush pattern of the earth like? the normal magnetic flux pattern, okay, whereby let's say this is the earth, this is the earth. You are going to have in the earth, you have south pole here, you have north pole here. Okay, what is the flux pattern? Moves from where? From north to south pole, right? So this one will be the flux pattern. All right, so the direction, always remember the normal pattern is from north to south pole. All right, just like that, just like that, just like that. Now let's understand Fleming's right hand rule. Fleming's right hand rule, remember, is used to determine polarity in solenoid and current carrying conductor. All right, so what is polarity? Let me even ask you, what is polarity? Polarity is the pole of the magnet. We have to know the north pole of the magnet and the south pole of the magnet. How do you know? It is through polarity that you know. That's why it's called polarity. So it's this instrument you use to determine polarity in those two devices that I listed. That's the current carrying conductor or the solenoid. Okay, so Fleming right hand rule. All right, this one is the right hand. Remember that is right hand. All right. All right, pardon my drawing. 1, 2, 3, 4. Okay, this one up. This one is the thumb. All right, pardon my drawing. So just know that it's your right hand. It's right hand that it normally is. So the thumb is usually what? The motion, okay, or the direction of motion. Direction of motion. That's the place that the thumb is facing determines the direction of motion. What direction? Does the flux? What's the direction of the flux that I was indicating with an arrow? For example, we have north pole here, we have south pole here. What's the direction from north to south, right? You can also have some magnetic field that flows from south to north. That's why you have to use something like this to know the direction of what? Of the flux from pole to pole. Okay, so but the standard is from north pole to south pole. Then this one, index finger. Index finger is, this one is the magnetic field or flux. Is flux. Let's put flux. Magnetic flux. All right. This is the magnetic flux. Then this one is the what? Current. All right. As simple as that. These two no join. Only these three. That's for the Fleming's right hand rule. All right. We have to also understand something like angle of dip. Okay, angle of dip, which is what? Is the horizontal angle. Okay, angle to the horizontal. So this angle, the angle to the horizontal is angle of dip. Another one is angle of inclination. Angle of inclination. Angle of inclination is the true angle to the north pole. Okay, true angle to the north pole. All right. Magnetic flux is a vector quantity. Sorry, magnetic flux is a scalar quantity, but and its SI unit is magnetic flux is a scalar quantity. SI unit is Weber. Magnetic flux density is a vector quantity, and its SI unit is Tesla, like the Tesla you know. So magnetic flux is usually given as magnetic flux is equal to B times A, where A is the what? Is the area. B is what? A is the area. B is the magnetic flux density. So B times A, that's it. This is the symbol for magnetic flux, equal to B times A. So if there is an angle, okay, if there is an angle among the parameters that you are solving with, what do? You put the angle. You now say cos, because we are working with something. We are working with horizontal here. Anything magnetic field is horizontal. Remember, I told you, anywhere you have horizontal in physics, you use cos. Anywhere you have vertical, you use sine. So cos theta. All right. Magnetic flow is equal to A times B cos theta. All right. Whereby theta is our what? Is our angle. All right. So let's look at Please do well to answer the questions. Do well to answer the questions found in the lesson notes. All right. So let's quickly look at electromagnet. Electromagnet works under the principle of electromagnetism. I already explained what electromagnetism is. All right. And its application is in crane, or its use is in cranes. You know what is crane? A crane is used to lift objects, to lift heavy objects. It's also used in relays. Relays is used to what? To transport current. All right. It's also used in electric motors and generator. /generator. All right. So that's that for electromagnetism or electromagnets. The uses of electromagnets. All right. Uses. Let's quickly digress. The strength of a magnet depends on some factors. Strength of a magnet depends on one. The first one is number of coils, okay, or number of turns in the coil, okay, number of turns in the what? Coil. The second one is what? The current. Is it high current or low current? The current flowing through it. Is it high or low? When the current is high, the strength of the magnet is high. When the current is low, the strength of the magnet is low. The third one is the what? The material used. Is it a soft iron core or is it steel? Material used. All right. All these are the factors that affect the strength of magnet. This material, you said, is it iron or steel? Or we can also say the nature of the material. Okay, of material. Nature of material. Okay, all these are expected questions. Don't joke with these questions. Don't joke with these. Okay, they are very, very easy to internalize. Very, very easy to internalize. Very easy to internalize. Understanding moving instruments, they are used to measure, current. Some instruments that are used to measure current. Okay, we have moving coil instruments. Okay, moving coil. And what? Moving iron. We have moving coil and moving iron. Okay, moving iron is usually sensitive. Okay, it's sensitive, but it is crude. Okay, it is crude. It doesn't have much application. But moving coil instrument is robust. No. I'm missing it all. It is this one. It is moving coil that is sensitive. Moving iron is robust. Moving coil is sensitive. Okay, such as moving coil galvanometer is sensitive to current change. Then this one is robust. This one can measure various types of currents. Moving iron instruments. For example, ammeter. This one, the example is voltmeter. Okay, then this one is ammeter. Voltmeters. This one is ammeter. All right. So that's that for that. So how do we convert a galvanometer to an ammeter? Converting a galvanometer from galvanometer to ammeter, we use what? We use shunt. Okay. Converting to ammeter, we use shunt. Use parallel shunt. All right. Parallel shunt. Then from galvanometer to voltmeter, we use multipliers. All right. Please, and these multipliers must be in series. Use multipliers in series. Okay. So how do we increase sensitivity in a moving coil or in all these instruments used for measuring current? How do we increase sensitivity in them? It's very easy now. Reduce the resistance. Reduce resistance. You know that when resistance is low, current travels faster. All right, and more current travels. Okay, current increase when resistance is low. So reduce resistance. That's the first one. Then the second one is ensure you have a strong magnet. Okay, So that's how to what? Increase sensitivity. How does a direct current motor works? We are going to look at direct current motor and alternating current motor. All right. Direct current and alternating current motor. So for direct current motor, DC motors, how does it work? Through what? Electromagnetic induction. What is electromagnetic induction? When motion is induced by electricity in a changing magnetic field. Motion is induced by electricity in a changing magnetic field. All right, when electricity is induced in a changing magnetic field. Okay, and who is the father of this? Now Faraday. Now Michael Faraday. Michael Faraday is the father of electromagnetic induction. Now looking at DC motor, the principle, when current is high, when current enters the field plus the magnetic field, what happens? Motion, you understand? Motion is induced. It gives motion. All right, motion. That is how the motor works. Current enter magnetic field, changing magnetic field. Motion is induced. It starts rotating or rotation. All right, for DC motor. All right, so if you use your Fleming's right hand rule now, for example, remember what we said, that the thumb represents the motion. All right, the thumb, this one is the motion. This one is the what? Direction of motion or direction of force. This one is the what? The current. All right, and this one is the what? Magnetic field. Magnetic flux, sorry, flux. All right, so Fleming's what? Is it Fleming's right hand rule we use for this thing or Fleming's left hand rule? It's the left hand rule we use for electromagnetic induction for DC motor. It's left hand rule, not right hand rule. We use Fleming's left hand rule. Okay, we use Fleming's left hand rule to determine the force and also the direction of rotation. All right, this one is the Fleming left hand rule. Can you see? So right hand should be like this, left hand should be like this. Okay, so don't forget that. What are the parts of the DC motor? Parts. Number one, we have what is called armature. All right, which is made up of what? The armature is made up of soft iron core. Number two, we have something called commutator. Okay, commutator. Here, the type of commutator we have here is split ring. Split ring. But in AC motor, alternating current motor, we have slip ring. Here, in direct current motor, we have split ring. In AC, we have slip ring. What is the function of this split ring? It converts what? It converts AC to DC. All right, that's the function of this. All right, or what they call that's the function of this split ring. Okay, converting AC to DC if there is a need. But what this split ring does is that it ensures that the current that is coming out is direct current. That is the major function. Okay, ensuring that the current that is coming out is what? Direct current. We also have part of it like brush. Okay, brushes, and also we have magnetic field or magnet. All right, these are the parts of a what? A DC motor. So the motor usually converts electrical energy to what? To mechanical energy. That's electrical to kinetic energy. All right. So how do we understand the direction of flow? If you are using a left hand rule, here is normally it's always the force now or motion force. Then here is the current, and here is what? Our magnetic field. Okay, it's just the same thing, just that it's now left hand rule, and here it's now labeled as the force. That's just the difference between left hand rule and right hand rule. The force, which is the what? The rotation, the motion. Now let's quickly look at induction, of which the same Faraday is the father. Induction. Like I said, in a DC, in a alternating current motor, you have the same components. Yes, but the difference is that instead of split ring, instead of split ring, we have slip ring in it. And the function of the slip ring is to what? To ensure that the current that is coming out is what? Alternating current. Okay, don't forget that. Okay, so induction, Michael Faraday is the father, and the Faraday's law of induction states that EMF is induced by a changing flux, a changing magnetic field. Magnetic field induces what? EMF. What is EMF? Electromotive force. Okay, represented in volts. What is used to measure electromotive force? Is measured with a potentiometer. We already talked about this now. A potentiometer is a specialized type of galvanometer used to measure EMF. All right. And what is EMF? EMF is the work done of the entire circuit. All right. But potential difference is the work done per load. Okay. So when the system is loaded, that is when we talk about potential difference between loads. But EMF is the what? The work done of driving current throughout the circuit. Okay. The force that drive current throughout the circuit. That's the work done in essence. So this pushes us into Lenz's law. All right. Because of what Faraday stated here, that magnetic field induces EMF. So the magnitude of the EMF, that's the strength. The strength of the EMF is directly proportional to what? Flux. All right. Or the rate of change. The rate of change of the flux. Rate of change of the flux. All right. That's what is going to determine the EMF. All right. Lenz's law states that the induced current flow in such a direction opposes the change producing it. It is the law of conservation of energy. It conserves energy. The induced current flow in such a direction opposes the change producing it. So it ensures that energy is not lost. That's Lenz's law for you. Okay. Conserves energy. All right. Let's look at something. Examples of where they are applied in. Okay, let's leave this one and look at eddy current and inductance. Inductance. What is inductance? Inductance can be defined as the property of an inductor. Okay, when an inductor opposes change in current by inducing EMF. So when an inductor opposes change in current by inducing EMF, it's known as inductance. All right, it's usually represented with L. All right, L. Inductors usually delays. They delay current. Okay, they delay current. It opposes change in current. It delays the current by inducing an EMF. All right, that's what inductor does. Its SI unit is what? Henry. H is measured in Henry. All right, that's its SI unit. So induction can either be connected in series or parallel. Just the same way you calculate resistors. It's the same way. The one for series, do it like that. The one for parallel, do it like that. Okay. The energy of an inductor is equal to 1/2 I square. Is it I square? The length is supposed to be L I square. Where L is length, I is what? L is inductor, not length. L is inductor, I is current. All right. So if you ask energy of an inductor, you use that. So what is the uses of electromagnetic induction? Is it inductance? Sorry. Where do we apply inductance? We apply inductance in filters. We apply it in motors and generators. We apply it in transformers. /various energy storage system. Energy storage system. All right, we're almost done with this class. I think we should go straight to eddy current. Eddy current. Eddy current. All right. Eddy current is the loop of current formed inside a conductor when exposed to a changing magnetic field. So during electromagnetic induction, eddy current is the loop of current that does what? That opposes EMF. The loop of current that is formed, eddy current. The loop of current formed in an electric system in a changing magnetic field. All right, that's eddy current. Is eddy current a good thing or a bad thing? It is a good thing. All right, it is a good thing though. So how do we reduce eddy current loss? Because see, let me even give you the application of eddy currents first. Let's give the application of eddy currents. For example, it is used in braking. Okay, braking circuit breaker. Such as you can also use it in normal brake. Okay, normal brake like no, this one is not circuit breaker. This one is in brakes, braking system, like to bring something to a stop, like in train. And roller coaster. You know that roller coaster something? That thing like be turning around like this, normally seen in the park. That's where you use it. Another place where you use eddy current is in heating. Heating for cooking. That's to induce the heating. Another place where you use eddy current is let me see if I can see another one here. You use it in magnetic damping testing / detection. Okay, magnetic damping. Okay, and so on and so forth. So these are the uses of eddy current. You can see that it's a good thing. So how do we, prevent the loss of this eddy current? How do we do that? Laminate iron core. Number one is what? Laminate core. Number two, thin the section of the core. Make it thin. Thin cores. Make the cores thin. High resistivity or silicon steel. Restrict current path. So that's why you have to make it thin. When the resistance is high, it reduces eddy current path. So one is to laminate the core. Two is to what? Make it what? Thin. All right. Take note of all of that. Let's look at the final part of the lesson, which is root mean value versus peak value. All right, root mean value versus peak value. Okay, for root mean value, because it's actually there's a relationship between both. So peak value versus root mean value. So this root mean value can be a current, normally represented in ROMV or ROM current. Okay, but let's say let's just put it as root mean current here. Okay, or root mean square. Let's say root mean square. All right, the ROMS. But that root mean square, that's the root value. Okay, so our peak is equal to the maximum. Okay, the maximum current. So peak current, remember the meaning of peak means what? Maximum current. Maximum current or volts. Then our root mean square is what? Effective. Root mean square is equal to what? Effective. The effective volt / current or current. The value. All right. Now, how do we relate them? Because both of them are equal to each other. So let's say we're working on volts. Volt root mean square is equal to what? The peak volt. Peak 1 over root 2. That's it. Therefore, when we inverse this, we are now going to have V root mean square is equal to root 2. No, it's going to be peak volt. Peak volt over root 2. All right. So this is what we are going to get. So this is the relationship. So if we want to solve now, we are using both. We put one here, we cross multiply, and we solve. All right. The way we solve, to remove this square, we can just easily square both sides. Maybe we cross multiply. We now have peak volt is equal to, we are cross multiplying, right? This times this. Give us peak volt is equal to this times this, right? We're now going to have root mean value. Maybe root mean value is 2 times root 2. Okay. 2 root 2 is equal to what? Likely 4. 2 root 2. Square and square root. Let's look at the final part of it. Remember, if you have something like this, you just have to square both sides. You square both sides and get your answer. Peak is equal to this. So you square both sides. You get your answer. Cancel. Then peak is equal to 2. All right. After squaring both sides. Thank you so much for taking this lesson. before we go, we are going to look at conductors. We are going to look at conductors. Let's just look at Einstein photoelectric equation first before we go. We can't just leave like that when we have some other, small aspects we have to touch. Okay, Einstein's photoelectric equation. We don't have time. Oh, okay, Einstein photoelectric equation. What is the meaning of photoelectric? First of all, let's understand photoelectric, and thermionic. Okay, photoelectric emission means the emission of electrons when light is induced in an object as a result of the triggers from light. That is photo and electric. Photoelectric. Photo, which is light, cause what? Electric, which is what? Electron. All right. Then thermionic emission is what? When ions are emitted as a result of heat. All right. Heat. When you heat a substance, it emits ion. That's what thermionic emission. Now let's look at the Einstein's equation of photoelectric. Einstein's equation of photoelectric. We have something like an HF. One is for Planck constant. The other one is equal to this minus Ke, which is what? Kinetic energy. Where H, F, this, and Ke. Okay, so this is equal to what? Kinetic energy. Kinetic energy. This is equal to what's this called? Work function. All right. This is equal to frequency. This is equal to Planck constant. Planck's constant. So this together, HF, as represented here, is known as what? Photon energy. Photon energy. All right. So Planck constant times frequency is photon energy. So you can make subject formula and solve what you have to solve. So Albert Einstein also has another, what is Planck constant? Is it not 6.64 times 10 raised to power times 10 raised to power minus 34? Is this not Planck constant? Hope I'm right. Let's look at the second equation. Okay, before we go, let's understand the meaning of work function here, because they might not represent it as work function, all right, and kinetic energy. So work function is equal to what? The minimum energy to release electron. Minimum energy to release electron. All right, then this one, Ke, usually represented as Ke max, is what? The maximum kinetic energy of the emitted electron. So the max Ke of emitted electron. Emitted electrons. Okay, so that's that for this. So what are the applications of thermionic and photoelectric? What are the applications? Thermionic is applied in vacuum tubes and cathode ray, while photoelectric are applied in solar cells. Solar, remember, photo gives us electricity. Okay, photo cells and photoelectric sensors. Anything concerning light to current. Okay, light to electron to form current from light, conversion of energy. Anything that involves conversion of thermal energy to ionic energy or to charge energy is for thermionic. That's why we have cathode ray tube there. Okay, and vacuum tube, cathode ray tube, vacuum tube, and so on and so forth. All right. Let's look at the second law about Einstein's law. It's called the law of binding energy. Okay, the relation of mass and binding energy. Mass and binding energy. Okay, E, which is the energy, binding energy, is equal to mass C squared. Or it can be E is equal to mass, change in mass. Okay, change in mass C squared. Yes, M is equal to mass. C is equal to what? Speed of light. Speed of light in a vacuum. In a vacuum, which is approximately 3 times 10 raised to power 8 meter per second. All right. So let's quickly look at conductor, insulator, and so on and so forth. But before we do that, let's understand the uncertainty principle by Heisenberg. It's called the Heisenberg's